Welcome to the second session in our workshop on high-throughput computing with Dask. I'm David Swenson, and today Willy Rath and Katharina Huflich will be talking to us about Dask Job Queue, which helps integrate Dask with your queuing system on HPC computing. So if you want to play along with some of this, we should say that the way this is going to work is that there's going to be a little bit of sort of more of a show and tell at the beginning from Willy about how to do these things. But then there'll be a time where you can sort of come along yourself and try to modify what Willy's doing on real supercomputing resources to work on a little toy cluster that we're going to have that you can have in your own computer, basically. And to do that, what we're going to ask you to do, if you want to do this part of it, is to install Docker and then the Docker containers that we've developed as part of the Job Queue features tutorial. So to do that, the URL at the top there is how you can find the instructions. If you scroll down from that, you'll see something that looks like what you see here on the screen, which describes installing Docker, Docker Compose, and then the setup stuff that tells you how to actually get these things specifically set up, including there's a start slurm command that you will need to run. So hopefully many of our participants have already done that. If you have not, I'll have a little time here to tell you about ECAM and CCAM, the organizations that sponsor this, as well as to give you a little bit of background or context for today's workshop. So CCAM, as I mentioned in the last meeting of this, is an organization with 50 years of experience doing various events to help the computational chemistry community share information, different workshops, schools, and conferences. It uses a nodal structure where nodes are typically associated with academic institutions. There are 17 nodes and growing, spread out throughout Europe, as well as one in Israel. ECAM is a European Union Horizon 2020 Center of Excellence. At ECAM, we're really focused on sort of preparing the world of computational chemistry for the next generation of supercomputers, for exascale computing. And so we do that through software development, training, and discussions with industry. Obviously, this is one of our training events. ECAM is made up of 16 CCAM nodes, 3 PRACE sites, a center for industrial computing, as well as 12 industrial partners. What we're working on here is what we would call task-based computing. So in task-based computing, the idea is that you program as a set of tasks. You design your program as a set of tasks where the output of one is the input to another. And this allows for some very complicated parallelization workflows. We talked about all of this last week, so I'm not going to go into too much detail on this, but just reminding what we're doing here. One of the great things about Dask as a package in particular is that it integrates with other packages like NumPy, Pandas, and scikit-learn. This is one of the main things we talked about in the previous session. And the beauty of this is that it makes it so that for a lot of things, Dask can just be a drop-in replacement for code that you've already written. I think Willy is going to really show that today, that for something that you might have just done with NumPy, you can instead do it with Dask, and with very little change in effort from your code, you get phenomenal performance improvements. So last time we talked about Dask, we talked about these integrations in the core library, we talked about how we would parallelize within one node. Today is where we really start to talk about high performance computing. And so today we're going to talk about Dask Job Queue and how you can integrate Dask then with your HPC queuing system. Dask Job Queue basically makes it very easy. If you have a sense of the structure of the nodes that you're working on, it makes it very easy to take code that you've written for Dask and run it on HPC clusters. Now, next week, we're going to talk about Job Queue features. So Dask Job Queue, of course, builds on Dask. Job Queue features builds on Dask Job Queue to allow some more complicated workflows like MPI within tasks. So this is sort of the levels of things that we're talking about here. Today's tutorial is going to be presented by Willy Rath, who is a research software engineer at Geomar, the Humboldt Center for Ocean Studies. And helping with questions, we'll have Katarina Huflich, who is also a research software engineer at Geomar. And with that, I will pass it over to Willy.
Yeah, thanks a lot. I'll just need a second to share my screen. And to make sure I can at least try and have a look at the Zoom chat. Now, I think everybody should be able to see a Jupyter Lab screen and my mouse pointer floating around. All right. So I think I've prepared materials for roughly 90 minutes. These will, and I've posted the link to the materials into the Zoom chat. So maybe Alan or can also post this to the YouTube chat. The agenda will be a brief intro, maybe 10 minutes, where I also give a tour of the docs of Dask and Dask job queue, because that's probably the main takeaway for most of you. Where can you find details on the configuration, usage, etc. of Dask job queue? Then the second part will be an example application of n-dimensional arrays that we'll use, that will start solving with NumPy. Then we'll scale it up vertically, so on a single node or a single computer, using a local Dask cluster, very similar to the approach that Jacob presented last week or 2 weeks ago. And then we'll scale out the same workflow horizontally to many nodes using Slurm cluster via Dask job queue. And there will be some room for questions, also for some hands-on testing with a Docker-based setup that David just mentioned. Then we'll see some, let's say, benefits of using horizontal scaling for IO-bound problems, and some more insights into the elasticity that we can achieve with Dask job queue. And then maybe as an optional add-on, we can have a look at some at least rudimentary functionality within Dask to be resilient against terminating workers or terminating resources. And then again, we'll have some space for questions. Having said space for questions, you are explicitly asked to raise any question you have immediately in the Zoom or in the YouTube chat, wherever you feel most comfortable doing that, or wherever you are watching this. And there, Katarina and also probably Alan and David will try and answer most of them right away. If there's stuff that I should mention also in the stream, or that I should demo, then Katarina or the other two will just interrupt me at some point where they think it would fit, and then I can also go back to the questions in the live stream. So let's head over to the tour of the docs. I think the most important URL to keep in mind is dask.org, or for just job queue, jobqueue.dask.org. But as job queue builds heavily on Dask distributed, and most of the concepts are only very slightly adapted from there, it's also a good thing to get yourself familiar with Dask, with the distributed docs, which are available here. Then if you want to install Dask job queue on your system, the two stable and recommended ways are, of course, using pip or conda. But as Dask job queue is, at least in some phases, under heavy development, and especially if you run into problems that are solved, for example, via the Dask job queue issue tracker, you may want to also install development versions of Dask job queue. This can be done again with pip, but then referring to the GitHub repository directly. As I said initially, getting help is, as always, it's a good idea to read the manual. It's for Dask job queue is also not too much, so you can just maybe take an hour and read it completely. Then something that is really recommended is raising users' questions on Stack Overflow and using the Dask tag. I think there's nothing that is specifically referring to Dask distributed or Dask job queue, but the Dask tag itself is usually a good place to ask. And then, of course, there's often lots of great support available on the Dask job queue issue tracker, and these are also very open to pull requests and active collaboration or contributions. Oh, there's a typo, and in the docs, there's example codes for most of the cluster classes that you can come up with. So there's examples for PBS and HD Condor, etc. Here, I'll focus on Slurm cluster because it's it's the cluster manager that I'll use in the live demo here. And the main idea is that if you followed Jacob's introduction last week or 2 weeks ago, he set up a local cluster that could fill up one machine, and he specified how many workers with how many threads and what the resources of these workers should be. And then he had a very simple way of submitting work to this cluster. In the HPC context, it's a little different. You basically specify the shape of an individual job. So you say, I want my cluster to consist of jobs that have 4 processes. That would lead, in the Slurm case, it would lead to the specification of the number of CPUs. Then this whole job should have, in this example, 16 gigabytes of memory available. It should be accounted for by this project, last for at max an hour, and be submitted to the queue with such and such a name. And then in the second step, you'd say, I want 8 of these jobs, and after some time, these 8 jobs will be spun up and will be combined into a Dask cluster. The above here is very close to the minimum that you need to specify if you want to start a Dask Slurm cluster. But there's a lot more to the configuration. There's, again, lots of documentation of the configuration of Dask job queue in the docs, and there's a great blog post on the Dask blog, which also has some insights on choosing the shape, let's say the size of threads versus processes, etc., of workers. Then something that you may also run into is debugging Dask job queue. For example, getting it to run at all. Often needs some insight into the specifics of the HPC system that you are using this on. And a good way to start is, again, the docs. There's some strategy for debugging Dask job queue, and I think the most important information is the job script that will be automatically generated based on the parameters that you gave for your cluster, and that is probably relatively easy to understand and to debug by anybody who's familiar with the HPC system. So if you run into problems that you can't solve yourself, have a look at the job script. If it doesn't help you, then you could take this to your admin, for example, and they'll probably find out if you did something that wouldn't work on their queue system, or if you used an interface that isn't existing, etc. And then while you are working with this, you may want to monitor what you are doing. And if you're not familiar with HPC job schedulers, in Slurm, we'll use the sq command, which gives an overview of all the jobs that are submitted to the queue. When we'll filter this to our username, then you can build something with Watch that updates this sq call every 30 seconds and displays it to some terminal. Or you can split this into different job states and just count the jobs with a specific pattern, which would tell you if you have many jobs waiting to get into the queue, which may explain why, for example, your cluster isn't really scaling out the way you wanted this. And then working with Jupyter, it's often a good idea to also have some process monitoring what the machine that Jupyter is running on does, which you can use top or htop for. Now, let me switch to the first real application. And I think I should take a minute to get everybody on board, because this will be the go-to example that we'll use through at least the next half an hour. Now, what we want to do is we want to estimate the number pi. And there's probably many different ways of doing it. There's dozens of ways of doing that. And that's a very bad and inefficient way of doing that, which is, however, very very instructional, and which is very easy to, which is a nice example that you basically can scale to any data volume. It always works the same. All it does is the more data you use, the higher the precision at which you can estimate the number pi will be. And the whole idea, okay, there's somebody who says the GitHub link doesn't work. As I have it open currently, I can post it again. Maybe I shouldn't focus on the chat too much for now. All right. So what we want to do is we want to use a Monte Carlo method for estimating number pi, and we will use for that we know the area of a unit square, which is 1, and we know from actually the equation for the area of a circle, which is pi r squared, we know that the area of a quarter circle within this unit sphere is pi divided by 4. So now if we randomly choose positions within a unit square uniformly distributed in both dimensions, and we count all the points, and we count only those points that fall below this unit, this quarter circle, then we can take the ratio of these points, all points divided, the red points in this image divided by all points. And we'll know that this ratio will approach pi divided by 4, the more, and it will approach pi closer, or pi divided by 4 closer, the more numbers, or the more points we draw randomly. So let's first do this with NumPy, and there's a function that we wrote for that because we want to basically see how, as we increase the amount of data that goes into this calculation, improves the precision of our estimate. Now, we draw a random array that is something which we use to exactly specify the size in bytes, comma 2, which is a two-column array of x and y in this unit square. So we draw this with a NumPy uniform random number generator, giving us numbers between 0 and 1. And then we square this and take the sum over the second axis, which means for each pair of these x and y's, we calculate the radius in this unit square. And then we compare the radius to 1, and we have a Boolean that counts that is true wherever we have a red point, and it is wrong, that is false wherever we have a blue point. Now, if we take the average over these Boolean values, then we know that this is pi divided by 4. So we just take 4 times whatever comes out of here, and we have an estimate for pi. I think I've already executed that. And now we could do this for example, 10 megabytes and 100 megabytes and 1 gigabyte of data. And we see that with 1 gigabyte and a NumPy that only uses 1 thread on a otherwise very powerful computer, it takes about 2 seconds and 1 gigabyte of memory use to estimate the number pi to something that some of you probably already see it's wrong after 3 digits. So what if we wanted to go for at least floating point resolution? Well, I said this is a very bad method for estimating pi, so never use that in production, but it is really illustrative and gives a nice toy example for sending arbitrarily large data workflows, to large clusters. Now, what if we go for 10 gigabytes? Note that this is on a computer which can handle this. But if you did that on your laptop, you'd probably already be out of memory. So with 10 gigabytes of data, we have to wait for quite some time, at least 20 seconds if we scale this up, but I think it's even more than that in the end. It's done now. So it takes 20 seconds, and it's really actually at the maximum of what we want to of what we can afford on a single computer. So we won't go to any higher. But what we're going to do is we are going to stop this kernel here, which is a good thing that you should do as well if you are following along somewhere. And we go to something that scales up vertically. So on the same node, by using Dask, this is now very close to what Jacob presented 2 weeks ago. So we'll import Dask distributed, and from Dask distributed, we create a local cluster with only one worker that has 8 threads. So we'll be able to execute 8 tasks at the same time. And this whole worker has 24 gigabytes of memory. So it's already very comfortable, but I think we can show off a little here because we have a big computer to play with. Now, ideally, this Dask dashboard plugin will be able to find this cluster. And on the right-hand side, we'll have a stream of tasks that are executed. Below here, there will be a few progress bars appearing, and I have a tab here that shows information on the individual workers in the cluster. And in this cluster, we only have one worker, which is listening on some internal network address. It has 8 threads, is not doing anything at the moment, also is not occupying lots of memory. And it could, in principle fill up to 22 gigabytes. Now let's put this into work. I won't go through this function in detail. I just highlight this one here, and maybe I should increase the font size a little, but I'm not sure. Maybe somebody from the chat can give me a hint if the font is too big or not. For me, it's a little too big for my small screen here, but I suspect that it's maybe for those following along, it's easier. All right, so maybe I can also make it one smaller, or is that already too ambitious? Okay, also fine, then let's stay there. So what we do is, originally we had the NumPy uniform random number generator, and that's actually all we need to do, or almost all we need to do here. We just specify the keyword arguments for this uniform random number generator as we did in NumPy, and also specify the size of the array that we want to request. But we need, or we can specify one more thing. We can specify the chunking, which here we choose with an argument to the function that calculates or that estimates pi. So we draw this 2-column array for x and y. Again, check whether x and y are below or above the quarter circle, and then we calculate pi as the average of all the points of the Boolean values of all the points, and because we know that this is pi divided by the number of 4. And then in Dask, we need to explicitly trigger computation, because this step will only define a directed acyclic graph that encodes how the desired result needs to be calculated once we request it. And then to get a handle on what's happening under the hood, we also have a look at the representation of the original data that won't really contain the data, but will tell us about the shape of the array, about the chunking, and a few more things. Now, let's go back to this 1 gigabyte thing. And remember, I think we had 2 seconds for that in the NumPy case. Now we have a worker that can have 8 NumPy calculations in parallel. And let's go ahead. First, so it not even took a second, right? The whole array is 1,000 megabytes or a gigabyte. We have chunked it in 10 chunks, so that leads to 100 megabyte chunks. And as you see here, the raw data, they consist of 10 chunks, which are 10 tasks, because each chunk is specified as please draw uniformly distributed random numbers with NumPy here. Now we can scale this up to 10 gigabytes. On the right-hand side, you see the progress bar that disappears after some point, and you see what each of the 8 threads of the worker is doing. Blue is, I think, the uniform random number generation and the aggregation of the sum over individual chunks, and then the yellow stuff is probably the normalization and the aggregation and the reduction over many chunks. And we see that even though we have 10 times more data, it only took twice as long than with a single NumPy array. And we can scale this out to some degree. So let's go for 100 gigabytes. On the right-hand side, you see that this is actually already also posing some effort for the worker. We can have a look at what the worker is doing here. It's calculating at 800% of CPU, which is exactly what we wanted, and it's occupying like 20% of the memory that it could occupy. And after some point, we'll get an estimate for pi, which is still not even floating point precision, even though we mangled like 100 gigabytes of data to get to this estimate. Now we could go to even higher resources. Maybe we could, as Dask can also easily handle bigger than memory calculations, we could just chew our way through this for hours on this computer, and then at some point reach a decent estimate for the number of pi. But we won't do this, but go for something that scales out to as many nodes as the cluster is willing to give us. Now I go to, if you're following along, I'm going to the 12_Dask job queue example notebook, which is to a large extent exactly the same as the thing I showed you earlier, but now replaces, if we remember this here, it replaces the distributed local cluster by a Dask job queue Slurm cluster. And I want this cluster to consist of Slurm jobs that have 8 CPUs each, 48 gigabytes of memory, and use them in one process. So we'll have workers with 8 CPUs and the whole amount of memory that we see here on the system I'm using that on. The queue we want to submit to is called cluster. I don't want these workers to live longer than 15 minutes, but they will be killed by Dask as soon as I close this notebook. Then knowing details of the system, I know that I need the IB0 interface to have a fast Ethernet, a fast InfiniBand connection to the other nodes and to the front end. And I know that there's a local directory on each individual compute node that is indicated in the TMP dir environment variable, where Dask is supposed, or any process is supposed to spill stuff if memory is not sufficient. And then after creating this cluster, I'll connect my client. I'll create a client within the process that is running behind this notebook here and connect it to the cluster. Now, before actually doing something with the cluster, let's have a look at the client. And it says it has 0 workers. And there's a question in the chat. So this is meant to be run from the login node. It can be run from the login node. And if you want to do this, then the network setup needs to be so for example, you need to choose an interface for the workers, which is specified here, that is able to see the login node. But in general, it's not recommended to run this from the login node. So this one here is running on a compute node as well. We are basically using a Slurm script to also deploy Jupyter on a compute node. And then we connect to this via an SSH tunnel, which then is tunneling via to the front end of this HPC cluster, and using the tunnel as a SOCKS 5 proxy, which we can then use to connect Chrome or whatever browser you want to the Jupyter lab. So in principle, you can run the notebook from the front end, but you should only do this if this is common practice on your HPC system, and usually because also the reduced data that Dask will return to you may be bigger than what the providers of the HPC cluster that you are on are actually intending to be handled on the front end. So in principle, you can do this on the front end, but you shouldn't maybe. Now, before looking any further, let's have a look at the queue. So under my name, there's one job. This is the Jupyter lab, that we see here. But there's nothing else. So there's no nothing resulted from this yet. to actually submit jobs that then will end up being workers in your Dask cluster, you need to scale the cluster. And we'll do this to have one job. Now, after some time, we see that we have a pending job, which is not available because of resources. That would actually be a bad thing. And I think we can try and circumvent this by going for smaller workers. And I suspect that 4 cores is probably available. So this is a shared tenant HPC cluster. So I'll just restart this and go for slightly smaller workers. So I use less cores and less memory, and try to scale this up again. And there we have a second job which is running now. And I think our Dask worker tab shows us there's one worker listening. And this is also what the RAPR of the client, of the Dask client tells us. So now I've shown this in the terminal here, but we see we have 2 jobs. One is from my Jupyter lab and doesn't have anything to do with Dask job queue, and the other one is the single worker. Now, what did Dask do here? It submitted a job script which is similar to the one I showed in the initial notebook. And here you can see that you basically recognize these 23 or 24 gigabytes of RAM. 4 CPUs, we only have one node requested. We want this to live for 15 minutes max. And then after setting this up, it will use the Dask worker command line call that you install with installing Dask distributed, and supplying keyword arguments, command line arguments to it that are necessary to specify, for example, where the scheduler lives, etc. Now, if we want to have more jobs, we can just call the scale method on the cluster again. Here I indicated I want 8 jobs. Now let's see. We seem to get a few. Let's see again. We have I have some priority issues because I played with too many very small jobs, but there will probably be some backfilling kicking in soon. And I'll have a cluster with at least 5 workers, totaling to 120 gigabytes of RAM. Now I'll define the calculation of pi exactly as we did before. I won't go into this again. And now let's see how fast we can get 10 gigabytes of random numbers for an estimation of pi. It's 2 seconds, so it's about 10 times faster than we had it on the single-threaded NumPy version. And it also looked like we have a lot more workers now. No, we have 5 still. So with 100 gigabytes is also no problem. And let's see if a terabyte takes too long here or not. And still with 4 workers, and you see they all max out basically the 4 CPUs that they were given, but they are nowhere near the memory limit that I've set. And we can see that calculating pi from a terabyte already takes some time with these few workers. Now I'll stop this here, and because we got less workers than I hoped for. But in your workflow, if you now work interactively, for example, with Dask, and you scaled out to 8 jobs, and now there's a time, I don't know, either you have lunch or you think about what you do next, then you can manually scale down to, for example, 2 jobs again. We'll see this quite soon in the worker tab, and we'll also see this on the batch scheduler. Dask will stop workers that are already active, and it will also cancel jobs that it has submitted, even if they didn't start yet. So now we have these 2 workers running. And of course, we could scale this up again now. Maybe not, now we know what we wanted to do, and we want the answer quicker than the last time. So we try if we get 16 jobs, which we won't now. We seem to be stuck with these 5 workers for now. And then we could repeat this calculation, or we could adapt something about it. Apart from doing this manually, there's a built-in elasticity to Dask, and which can also be used in Dask job queue. Now maybe let's go for 6 jobs and 1 job minimum. So I'll tell the cluster to not have a fixed size, but to adapt to the work, to adapt its size to the workload. And I'll tell it to have at least 1 job running all the time, and to scale out to 6 jobs whenever it thinks sufficient, whenever it thinks it's necessary. Now, the first thing we see is gets rid of all the jobs that are more than the 1 worker I specified to keep. And this is because there's nothing to do yet, right? And now let's do a very cheap calculation, estimate pi from 10 gigabytes, which was also feasible in a reasonable amount of time on our single node cluster. And now we see that it scaled out already to 5 workers. Okay, that's a little. So let's go for a smaller workload then. Let's go for 1 gigabyte. So if you have a very small workload, then the Dask cluster won't change size. Okay. But if we go for a bigger workload, and now maybe this is a good time for the cluster map, which you may have seen in Jacob's presentation 2 weeks ago. So this cluster map shows us, this is the scheduler, and it indicates what the scheduler is doing. And this is a worker, and the color coding of the worker will be the same as the color coding in the task stream and the progress bars. And there will be some information about communication between the worker and the scheduler, and as soon as there are more workers, also between the workers. So now let's submit something with a terabyte of memory. I've increased the chunk size with a terabyte of data in total. I've increased the chunk size, the chunks, in order to make them smaller. And this is because I adapted the total amount of memory available to the Dask workers to account for reduced availability of the cluster. Now, if we submit that, we'll see that it takes a second for the work to be defined. Then 1 worker starts working up here, and the progress bars move relatively slowly. But I don't know if you noticed, because it was very fast, but now Dask submitted 6 more jobs, 5 of which, or 5 more jobs, we had 1 already running, 5 more jobs, 4 of which started immediately. And you see that they basically take turns in, I think the blue stuff is drawing the random numbers, the yellow stuff is calculating and also keeping the partial sums, and then the end there will be one aggregation part where all workers are supposed to send the information about the partial sums to one other worker, to one of them, which then will actually do the final step in the calculation of pi. And while this is running, I'll have a look at the chat, whether there's any questions I need to tackle. Oh yeah, Katarina already responded to that. There was a question in the chat. Maybe I say it again also for the YouTube chat, or for the people on YouTube. There was a question asking whether there's a way for Dask if you run a local cluster in a Slurm job. If there's a way for Dask to find out about the resources that are granted for the Slurm job, and then to adapt to this. And Katharina said it has to be manually specified, and I think that's the most robust way to do this. I have seen clusters plus managed to convey the information about the allocated CPUs and the allocated memory to the Python process that is running inside there, but it's not very robust. So it may work or it may not work. And I think this is one reason for why you should specify this yourself. The other reason is, and we can get back to this in a minute, shaping your workers needs to be done with the problem you want to solve in mind. We can in a minute try and find a worker setup that is very bad for the problem you want to solve. So you can make stuff faster if you choose a wise shape and distribution of resources in your Dask cluster, but you can also slow it down. So I would actually advise against delegating this to the Slurm job, but to do it in a somehow explicit way whenever possible. So now we've seen that I think in the end there were 6 workers, right? So we saw that getting 1 terabyte of data through this Monte Carlo estimate still resulted in a very bad estimate of pi, and took 6 minutes. But we also saw that once this was done, the Dask cluster silently reduced to only the 1 job that we wanted it to keep running at all times. Now I'll shut this down. And I think we're at a point where we can have a few more questions. Now this is difficult. I can see if I can also have a look at the YouTube, which is now fancy, producing fancy images. But maybe Katharina or the others can indicate whether there's something that I should address in the chat, in the live stream. Otherwise, I'd make this, let's say, a Dask. I think we have some room for a configuration exercise, which we could use to also have you follow along in the Docker-based setup that Alan prepared. Now, I'm not sure how many are trying to follow along. Maybe you can indicate this in the chat. But the Docker-based setup that Alan and David were preparing, and for which the instructions have been posted on both chats, I think. This will spin up a Slurm cluster on your laptop or workstation or whatever, with only 2 cores. So with only 2 possible jobs running at the same time, and each of these jobs can have only 1 core and only 512 megabytes of memory. I think they are living in a queue that is not called cluster. They don't know anything about an interface, and they probably also won't be able to use any local directory. Yeah, cores, memory, and interface. Then in the I'll just type this here, okay? So short exercise, adapt the below to 1 core per job, 2 jobs max, 512 MB memory per job, queue name named batch, and no interface, and no temp dir, no local dir, And I think if you, this is not, yeah, down here, the user is not set. The user variable is not set. And maybe Alan can remind me, I think it was slurm underscore, slurm user. And username, slurm user. So if you just want to just execute this, you need to set an environment variable, which in Python you can do with import OS and then OS environ. Do this once, and I need to restart the kernel. Environ user equals slurm user, which I won't execute here, otherwise my username will be overwritten, and I'm not sure. The variable with my username will be overwritten, and I don't want this. So I'll make this non-executable. Okay, so I think I'd give 2 minutes or 3 minutes, and then I'll start implementing this here. At least I'll start making the job very small. The job's very small, and then I'll start adapting the workload that we send to these, and see if we can also use these tiny jobs on our cluster in a nice way. Alan, I'm not sure what you mean by dynamically updating the wall time.
I mean, after you declare the cluster, is it possible to change values inside, or is that, I actually wasn't sure.
There is probably some non-robust way of doing that. We can have a look. So I think there's the cluster has some internal arguments, and one of which maybe wall time. It's not here, but we can have a look at the job script. But then I think, all right, so there's a dummy job. There's a job script. And in header, there's a header. So in here, there's a job header. And it contains the wall time. So you can probably do this, but you shouldn't, because it's some internal functionality of how Dask job queue at the moment and within this particular version is handling the wall time. You can probably also find this string somewhere in the internal attributes. What there is, I didn't prepare anything on this. There is a way of specifying some fuzzy wall time and of making sure that jobs that die are restarted. I need to refer to the Dask job queue issue tracker here, or maybe Katharina or Alan can look this up. I think there was some recent discussion with Guillaume and Luik on this. Or recent, let's say half a year ago. And the strategy there would be that if you start 16 jobs all lasting for half an hour and you want to work for a longer time, maybe starting jobs with a short wall time would be nice to fit into small gaps in the cluster usage. So it would be good to, from a resource availability point of view, but then you don't want all these workers to suddenly stop at the same time. So there is a way of staggering these end times of the worker, of also letting the worker know how long it's supposed to live. And so you can basically have a smooth transition when one of the worker dies. Another one with a fuzzy end time will be started, and you can basically make your way through a full working day with jobs that approximately, say, let's last half an hour, but never all die at the same time. I'm not sure if this was what you're referring to, Alan, but in principle, it's difficult to reconfigure attributes of the job queue cluster once it's created. There is ways by using the internal API, but this is nothing that you can easily that you can trust to be working 6 days or 6 weeks or 6 months from now. Now let's do this here. So even though I see that there's people still struggling with the example setup, I'll go ahead and make this here a very small job queue cluster. So we can have 1 core per job, and we'll go for, let's say, 500 MB, just to stay below this. And we only want 1 process per worker, or 1 per job. Now this is batch. I won't change this. I also won't touch this. And in the setup that you are using, you also need to comment out this, but I won't do this because I need it on my setting, on my system. And I'll, just to be on the safe side, I'll restart this whole process here and also skip these steps. Now I have a cluster which is very small. Which is consisting of jobs that are very small. You see 1 CPU, 477 megabytes, etc. Nothing in the client yet. And let's see, it's probably relatively easy to get these up and running. They are all there immediately. Okay. They take some time because they are on a distributed file system. And distributed file systems don't really like Jupyter and Python and Dask, because they don't like too many metadata operations. Now we have these 16 jobs running. I've done this already. And we have a client with 8 gigabytes of memory spread over 16. Now we can skip this. And let's go on to calculate something. This clearly will fail. So 10 gigabytes we need chunks of at maximum, like, let's say 100 megabytes. Okay. So let's go for 1,000 chunks and see if Dask can handle this. It's looking good. Okay. Can also go for 10,000 chunks. Let's see how far we can take this, because at some point, I think this is also something that Jacob was introducing, or what was telling you in the last session. At some point the logistics for handling, and I'll close this cluster map here because it's will be difficult to handle these 20,000 jobs, these 20,000 tasks. Now, at some point, each of these tasks has an overhead of in the millisecond range, and at some point, the milliseconds from 20,000 or from hundreds of thousands of tasks will make up for most of the wall time. But in principle, we can create a Dask cluster from very small, from many very small, from very small jobs. I'll scale this down again, and then I think I won't go into the rest of this. Now, if you wanted to play with, maybe we should do this here. If you wanted to play with an elastic cluster, you can go between 1 and 2 jobs, because it's all your small Slurm cluster will be able to handle. And we'll see that this is in principle it's probably going to scale up now, but it won't go further than 2. And it's also kind of undecided if it really needs the second. And we'll get into more slightly more details on the adaptivity in a minute. But before that, I want to go to other ways of profiting from distributed computation, even if you are not CPU bound. So I'll stop this here. Shut down the kernel in order to free up also memory on the node that I'm running Jupyter on. And I'll go on to the distributed I/O notebook. Now, if you are in a distributed file system, you usually have many compute nodes that try to talk to networked storage nodes. And at some point, the major bottleneck for communication between an individual compute node and the storage system will be the network link, or the communication between the compute node and the storage system. So if you are in an I/O bound world, for example, where you need to read lots of Earth system observation data from disk, or lots of ocean simulation data from disk that you produced in a large simulation earlier, then often CPU and memory are not really a problem, but getting the data from disk into memory is the major bottleneck. And you can solve these by scaling out to many HPC nodes, because many HPC nodes will be able to use many network interfaces to talk to this distributed storage system. So, but before that, let me also introduce some convenience technique for handling some other convenience keyword argument to the Dask job queue cluster. If you have a look into your notebooks directory after starting a few jobs, you'll see that because you are running this Python process that handles the job queue cluster within this directory, you'll see that all the logs of your Slurm jobs end up there. And this is often, initially it's a good idea because you can have a look into them and you can see, maybe we should do this, and you can see let's have a look at the 720 out. And you can use this for debugging. So you should know where these go. But once they get annoying, and if you play with large clusters that you scale up and down often, then you will have dozens or hundreds or thousands of these log files. And so what we're going to do is we're going to find out where this is running, create a Slurm logs directory, or create a string that contains a path to the Slurm logs directory. And then we'll tell the Dask job queue cluster to store logs into this log directory. And Dask will make sure that this directory exists. Now, if we do this, there is this, I need to refresh this. There's a Slurm logs directory that doesn't contain anything now. I've told Dask to scale to six workers on 6 individual. We only got 2. Let's see. There's 3 which are blocked because of priority, which probably means that we'll be able to get a few more by the backfilling. But let's go ahead with these 2. So we have 2 workers living in 2 different nodes. And what we're going to do is we won't use the pi example anymore, but we'll use just some random data. We'll get normally distributed random data with a size of 100 gigabytes. So I divide by 8 because we have double precision here, 100 gigabytes. And we want chunks of 200 megabytes. And we can have a look at this in this nice Dask array representation. And we can use the ZAR store backend in Dask, in Dask array, to write this to write these data to disk. I used random data because I don't want it to easily be compressed. So we really can have an idea about the about the communication necessary to get the information to the distributed file system and back from the distributed file system. Now, these notebooks live in a distributed file system. I just dump it to some location within the notebook directory. If you are on a cluster where your Jupyter Lab is not running from the large scale distributed file system, you may have to find a different path here, but the idea is probably still understandable. So what happens now? Dask is going to create 500 NumPy arrays with random data and write them to 500 chunks in a ZAR store. It will try to compress these, which it will probably mostly fail on because random data are difficult to compress or impossible to compress. And at some point, we'll have a ZAR store consisting of 500 individual chunks that makes up, in our case, 89 gigabytes. And now we'll open this again, just to make sure that we don't have any data in memory. And we try to read it completely. And because we don't want to just put it into memory, we don't want to do something with it, we will perform a very simple and a very cheap calculation and just find the maximum value among all these normally distributed random numbers. And so until here, this defines the calculation, get me all the data, get the maximum of all chunks and for each chunk, and then get the maximum of the maxima. And with compute, we tell Dask to immediately execute this operation and return the result. Now, we see that okay, that took 5 seconds, which already is not too bad. So it brought approximately 20 gigabytes per second. And now it's still 5 to 6 seconds. Let's see how many workers we have. I think it's still 2. Yeah. And let's scale down to only 1 and see the effect on. So first we see that we only have 1 worker. Then let's open this pointer to the Dask store again, to the ZAR store again, and repeat the calculation. And what I hope to see now is that I/O from only 1 node is only half as fast, or takes twice as long, approximately at least, than from 2 nodes. And then just so you believe me, let's have a look at this task stream here. And so the length of these rectangles here in the task stream, is proportional to the time in milliseconds or whatever unit it took to execute this task. And the dominant picture here is the blue from ZAR steps, which almost always take about 200 to 300 milliseconds. So we don't see any significant effect from having more CPUs available to find the max, but we really see that the majority of the work done here is from I/O. So if we could scale this out to an even bigger cluster, which I think won't be possible now. We could increase the bandwidth with which we can retrieve data from disk even more, and at some point probably hit the limit that the distributed storage can offer. But as I won't get any more workers here, I will stop this. Now there's again maybe some time for questions, but I don't see any in the chat. So if you want me to go into something that you want to know, then this would be a good point in time to do that. Otherwise, I'll go on and have some more insight into the adaptivity. Okay, there's a question about scaling horizontally versus scaling vertically. I'm not sure if this is really a fully established throughout the computational science community, but vertically in the Dask world means on a single computer or on a single node. So vertically would mean buy a bigger RAM, buy a bigger memory for your laptop, or buy a faster CPU, or use more of the CPU on the laptop. And horizontally, in this terminology, means to more than one computer or to more than one node. So that would mean that with either with a threaded NumPy or with a local cluster, you'd scale vertically, and which also in the data center sense would make sense, right? Just put more into the CPU tower that you have there, into the gaming PC that you have there, and if you scale horizontally, you'd need more nodes or more systems, or you could even scale to more than one CPU, more than one APC cluster, if you find a way for these workers to see each other on the network. And I see Alex says it makes sense. Okay, so whenever I say vertically, I mean get more resources on the same node, and whenever I say scale horizontally, I mean go out into the cluster. Okay, so I think I showed this earlier in the Dask job queue example, but here I want to stress more the elasticity and the adaptivity of Dask. We'll again create some, let's make these a little smaller in order to make it easier to get more of these workers. We'll create a Dask cluster and request one job initially, which hopefully we'll get quickly. Yeah, there it is. Well, let's go for 8 jobs and just remind ourselves of what we did earlier. We have this NumPy estimation workflow, and to warm things up, we'll quickly calculate pi from 10 and from 100 gigabytes. And we'll see that if we scale up the cluster to 16, so twice the amount of workers, that the cluster will go even faster. But especially if we want to use Dask in an interactive setting, then it's probably a nice touch if you can make sure that you free up resources as soon as you don't need them. So what we're gonna do here is we'll make Dask adaptive again, and do so in a way that specifies more than just the minimum and maximum jobs number. So there's a minimum and maximum which refers to workers, and a minimum jobs and maximum jobs which refers to jobs. And I like to think about Slurm jobs instead of workers, because then I need to remember how exactly I specified this. Now what I also specified here is a target duration and some wait count, and the internal behavior of Dask is that every second or so, it checks how long am I calculating already on everything that's that the scheduler is executing, or that the scheduler is handling at the moment. And what's my target duration? And if the target duration is bigger than the amount of time Dask estimate from the history of the calculation it will take time to finish, then it will decide to increase or decrease the number of workers. Now there's, I'm not sure if it's a bug or just some weird way of implementing that, but this target duration is counted in CPU seconds. So if we have a worker with 4 cores, then 20 seconds would mean 80 CPU seconds. And we want this to take approximately 20 seconds on the wall clock. So we'll need to tell Dask that we want whatever calculation we give it, we want it to be finished within 80 CPU seconds. And then whenever Dask finds itself idling, it will scale stuff down. And sometimes it's a little too aggressive there, because workers need to shut down before they shut down. They need to send away their data to the scheduler, to a different worker, or to the front end process. And I think the default is to wait 3 times 1 second before it kills a worker, and we want this to be slightly slower. So we tell Dask to wait for 7 cycles of whatever internally it uses to estimate the workload on the cluster, and only after 7 idle cycles to send a kill to a worker. Now, I think I've reduced the memory that we have there a little. And I think we can also, again, use the cluster map, because it's really nice to look at and to see the cluster scaling up and down, or out and in, probably. So let's submit 100 gigabyte workload to the cluster. Initially, 2 workers are fine, and then it notices that it needs a little more than these 2 workers, and it submits a few more jobs. I'm not sure if and it only submitted now. This time, it estimated that with 4 additional workers, it will be fine. And it at least approximately met these 20 seconds. This is not really perfect. Now let's go for a bigger workload. And again, because I reduced the memory amount available to the workers, I also have to increase the number of chunks to make the chunks smaller. So let's go for a bigger workload. Now this would clearly not be feasible with 5 workers within 16 seconds or within 20 seconds. And Dask notices this and goes probably for the full maximum of jobs I specified, and it won't get all these. But we'll see that once the calculation is done. So Dask will try and get as many workers as it needs to finish whatever it's doing now within the next 20 seconds. And let's see whether there's more jobs starting. No. But I think you already see that with a moderate workflow, Dask only scaled out moderately, and with a bigger workflow, Dask scaled out more aggressively. And now we could, but I won't do this because with these few workers, it's not really fun to do so. But what I will show is, once this is done, Dask will get rid of all the workers immediately, or within the 7 seconds that we specified. And so it took a minute because it couldn't get enough resources to finish within 20 seconds. But if we were able to really scale out to, for example, 50 jobs or so, then the terabyte workload would be done in 20 seconds as well. And as you saw, it got rid of all the workers it didn't need quickly after the work was done. I'll shut this down as well. And by at least briefly reading over the chat, I think there was a question by Rohit. What happens if the job time ends during I/O? And this is, I think, touching on an issue that I wanted to go into next anyway. So if there's no urgent questions, maybe Ellen or Katerina can point me to something that I don't see in the YouTube chat. I'll go into exactly the points that are discussed in the Zoom chat now. Resilience. So Dask is able to cope to some degree with disappearing workers. I've linked parts of the docs on resilience. What we're going to do here is we'll create a Dask cluster, give it something to do that takes a long time, and kill workers while we go, and see how far Dask can cope with that, and when Dask will start getting into trouble. Now, with respect to time, I think I'm 75 minutes in, so I just go ahead. I think we are well well underway. So again, I'll import Dask and Dask distributed and Dask job queue. I'll create a Slurm cluster, and again, I make this a little smaller because we really don't need these big. And I'm not sure if that helps, but we can also make it a little less ambitious with respect to the wall time. And now there's a trick that Katarina already was referring to in the chat. In older versions, I think there was some work to include that in the scaled behavior of the cluster, but at least there is, to my knowledge, no robust ways for a cluster that you scaled to some given size to recover to that size. And I think the best thing to keep in mind, the best way to keep this in mind, is that the scale call to the cluster is actually imperative. It tells you, make yourself 8 jobs big now, and then it won't put any expectations about the future. It just tells you, get 8 jobs now. While the adaptive call is declarative, it tells you your state at any point in time should be between minimum and maximum number of jobs. One way to have a, let's say, a recovering fixed size cluster is to set the minimum maximum equal, and that's what we'll do. We'll say have 8 jobs, and make sure you have 8 jobs, no matter what happens. Okay. So let's first see if this works. We have sq $$ myself, and we'll just get rid of one of these. Let's cancel this. Now, if I had return here, one of these jobs will disappear. And after some time, Dask will notice that and submit a new one. Didn't do so. Yeah, there it is. Okay, so we can use this declarative way of shaping the cluster to have a recovering cluster. Now we have a cluster with 8 workers, 32 cores in total, and almost 100 gigabytes of memory. Again, we go for the NumPy workload, but now we don't do the calculation, but we just define how we compute pi. And this is because I want to, between the definition and the, so what we did earlier, let's go back for a second. What we did earlier is this function here defined the calculation, triggered the computation, then .compute in Dask blocks until the computation is fine, and then it returns the result of the computation. What we want now is we want to submit the computation, then manipulate the cluster by killing workers, and see if Dask can cope with that. So I rewrote this to not include the triggering of the calculation within the definition of the computation, but we have a step where we need to do this explicitly. And just to warm up things again, let's use 10 and 100 gigabytes for estimating pi. And we see that this is working fine and taking some time. This is attended. And so an alternative way now is just define pi. As you may notice, nothing happens on the cluster, but we have a Dask array that knows how it will be calculated, a Dask array of shape 0, because pi is reduced across all the rows of that 2-column array. Then we tell the Dask client to compute pi, which will return a future object pointing to the calculation. And then there's a method that tells us, is it done yet? Are we done yet? Are we done yet? No, we are not. And we can also see that here. And only the result call will be blocking. So only if we request the result of the computation, our prompt will wait until the result is really available, and then return it to us. So now we need a way of having workers die. But first, we need a way of knowing about our workers. So I've written a function which is called getCurrentJobs, which gives us the job IDs of all the workers that have Dask, or of all the jobs that have Dask in their name. And I just assume, because this is the only thing I'm doing on the cluster at the moment, I have these 8 jobs here. And then I want to be able to kill a few of them, but not all. So I mark the first 4 of them non-preemptible just by keeping them in a list of basically sacred jobs that I won't touch. And I'll have some convenience function to filter all jobs that are currently running for those that are not in a non-preemptible list. And so I have a function that gives me jobs that I can readily kill at all points in time. And then I use the random module to choose among all the preemptible jobs one randomly and kill it via sccancel. And I use some Jupyter magic here, so that probably won't work in a pure Python script. So I start this. I define this, and I think I need the. Let's see how it works first. So I need some sleep function in order to get the timing right, because I want to kill jobs only every few seconds. And now what I want to do is I want to see all the preemptible jobs. I want to randomly kill one of them. I want to wait for a second, because sccancel may take some time to actually have an effect. And then I'll try to get the preemptible jobs again, and I hope that this will contain one less. Okay, and this is the case. And we see that there's a canceling job, which is probably gone now. Now I define the calculation of pi again. I use a very big calculation. I use 500 gigabytes of data, and I chunk them in many chunks because I want this calculation to be artificially slow, so we can see what happens if we kill a few resources while we're underway. Now I submit this computation, and the cluster will start working now. And then I start a loop that waits for 5 seconds and kills a worker, and then it every 10 seconds will try and kill a worker. Now I did that. We are down to 7. Now at some point, Dask will try to recover from that and add a new job. Our random worker kill routine is doing its job, and got rid of another worker. Now the Dask cluster worked against this and submitted a new job, etc. And if we are lucky, at some point, we'll get a result. But what happened here? We already get a key error, which indicates that a worker was lost before it was able to submit stuff. And at some point, our pi calculation fails. Now what happened? We saw that in principle, Dask seemed to be fine with that, right? So if you look very carefully, then you saw that these progress bars, they were set back a little whenever a worker died, but Dask didn't really seem to care about this. What Dask does initially is it has some resilience, and for each task, it has an attribute. I'm not sure what it's called. I think I've suspiciousness, or I'm not sure if it's really used in the code. So it counts how many a task is around on a worker. It can't really say whether the task caused the trouble, but every task that was assigned to a worker, when the worker got in trouble and died, is marked suspicious. And after this task was marked as a suspicious task for 3 times, it's marked as an error. And so you can try and catch these errors in some low-level implementation, for example, using futures and delayed. But if you use Dask array, then the whole array calculation will be in an error state as soon as one of the underlying task is in an error state. And there is a way of increasing this 3 to whatever value you want to do. This is internal API. There is also, I'm not sure if that's already robustly implemented, But there is a way of configuring this. I'll just use the low-level internal non-recommended API here and set this maximum suspiciousness counter to 1,000. So I'll only consider a task to be impossible or to be problematic after it was around when a worker died for 1,000 times. And now we'll repeat this. Well, first we see the scheduler is freed because the object we call pi that initially pointed to these tasks on the scheduler was overwritten by something new. And so we define the calculation, wait for 5 seconds, kill a worker every 15 seconds, and see how Dask holds up. Now, while this is executing, maybe we can have a quick survey in the chats. So how many of you are working on HPC systems which provide ways of marking jobs as preemptible? So in your HPC system, in your Slurm setup, for example, is it possible to submit a job that is marked as preemptible by the job scheduler? I know of one German HPC system that I was working on, which at least explores this by allowing people for submitting preemptible jobs that then can be killed without notice by the job scheduler at any time, and they make this attractive to people by only accounting for 50% of the cost the job would have if it was a regular job. So is there anybody who worked on preemptible systems in the HPC world before? Okay. There's one, at least in the Zoom chat. Alex says that he is on a shared cluster which allows for preemptible jobs, and I'm not sure if there's anything in the YouTube chat. Not yet, but then there's also nope. All right, where were we? Dask is still not done. Yeah, so what we see here, in principle, Dask is able to cope with dying resources, right? And you can probably also find some sweet spot where Dask will be able to finish. But if we look at the no, we shouldn't do this here. Okay, so I'll stop this here. Okay, you see that it's essentially it can go on forever, and I think what we also saw earlier, it's from a Dask perspective, it's okay if, or at least with a built-in high-level data types, it's okay if resources die from time to time, but if they really die aggressively, then Dask will have a hard time recovering from that. Now, why is that? Just if there was interaction with the people in the stream, I would ask, why is that? Is there maybe a way we can reshape the calculation to be more resilient? Now, at least we see that after many of these errors, we get to some number pi, but we should ignore all this and so size in bytes is 10 megabytes, and we want only 10 chunks. Okay. Now I can persist this, which will calculate pi and then put it on the cluster. And the nice thing is we can then use the built-in graph rendering to have a look at what the cluster does. Now this is the dependency graph of of the calculation we just submitted. Down here, there's the division by 4. No, there's the division for the normalization of the mean. And then we have the aggregation of all the sums in the average over the Boolean values that indicate whether the point we picked is within the unit circle or not. This is split into many levels, and further down below we have this uniform random number generator that is calculating the data that we base our calculation on. Now, it's not currently implemented, but it would be if you want to rely on Dask arrays, and you want to work in a setting where Dask is on a partially or fully preemptible cluster, then you clearly would avoid tasks that are further to the right in this hierarchy to end up on workers that may be preempted soon. While you could easily cope with worker preemption in the deeper ends of the dependency graph. This is just so maybe one or two of you may at some point end up contributing to Dask or building stuff on that. So if you want to build software that can be resilient against dying resources in a more robust way, then what you'd need is a way of specifying that the higher in the graph, the more reliable the worker needs to be. And there is ways of specifying resources that are attached to workers or other properties. And there is, at least using the delayed and future way of handling Dask workloads, there's also a way of flagging tasks, so they only end up on specific types of workers. So you could use this to build something that is fully resilient, that has a few reliable workers that end up storing the information or keeping an eye on the information, that if lost will get us to fully recalculation of large parts of the graph. And you could also have workers that are more probable to die, and that would only handle the more ephemeral data. There's a question if Dask allows for dynamic moving or reordering of tasks. I'm not sure if I understand this correctly, or maybe it's so Dask is not the scheduler. Actually, it's relatively dumb in Dask, and Dask is created with a paradigm that makes workers greedy rather than a scheduler having too much power. So the way Dask handles the calculation is the scheduler knows about all the tasks, and the workers are greedy for tasks, and they are relatively reluctant to send away tasks to other workers. And what happens during the calculation? The scheduler has a pool of things to do. The workers all try to get their share, and so this leads to an initial distribution of the task, and then the workers start to calculate. And if there's a worker that's very busy and has many tasks, then it's less reluctant to send tasks to other workers that request or that try to get tasks from this worker. So if you have a very greedy worker that is not doing anything at the moment, and you have a very busy worker that is less reluctant to free or to send away some of its tasks, then the greedy worker will be able to get it. So in that sense, there's usually there's some automatic but less deterministic movement of tasks between workers. On the other hand, the workers also decide what they do next, and there's lots of work happening on the Dask side, and lots of development happening over the last few months. Now that also Dask has some really full-time employee developers, etc., where they try to group give tasks priorities and an order of execution that makes it, for example, more likely for this part to be finished before the next part starts, etc. Now, I think currently it will go through levels of the Dask graph. So all the workers will try to work to get all this done, and then all the workers will try to get all this done, and then this, and then this, and then this. But there's more and more internal ways of tweaking that, and there will maybe in the end or in the future also be ways of exposing that to the user, which I'm not really involved in. Okay, is there any other question I need to be aware of? Otherwise, I think we are well into 90 minutes. And that may be it from my side. A good, maybe just a minute, because I think this is really the most important takeaway. If you take anything with you, I don't know, if you have a notebook where you write down stuff or so, or maybe you take 5 minutes after this to jot down a few notes, then the most important thing to look at is the 002 of the docs notebook that I included here. Because this is basically having all the pointers that may help finding the information that you need if you run into problems. All the rest is just getting the concepts into your head, which I hope we succeeded in, and then really remember to where to find the information if you need it. All right, and I see David already switched on his camera, so I'll stop my screen share.
Well, we can see if there are any questions that might be worth showing.
Wrap up
your screen on. Are there any other questions? As Alan,
yeah, we can also. Yeah, right. I can also switch it on again.
As Alan said, it's okay. We're turning off the screen. So, well, thank you very much, Billy. I guess we're now going to just do questions in here. Alan, is that the idea?
Yeah, I think that's the idea. We'll give people a chance to just talk freely, right, without being recorded, right? So,
okay.
So I'll just turn off the screen, the stream now.
Right. Well, again, thank you, Billy and Katharina, for helping with the questions. And then I guess we'll have a few more questions here in the Zoom for anyone who's here. If anyone on YouTube has any questions, please post them and we can try and get those answered immediately. But it looks like there haven't been many questions there. There's mostly things here.